The launch date is approaching for the smallest spacecraft hitching a ride on the most powerful rocket ever built by NASA. SwRI's first CubeSat mission will analyze space weather. What is a CubeSat and why do space scientists want to learn more about conditions in space? That's next on this episode of Technology Today. We live with technology, science, engineering, and the results of innovative research every day. Now, let's understand it better. You're listening to the Technology Today podcast, presented by Southwest Research Institute. Transcripts and photos for this episode and all episodes are available at podcast.swri.org. Hello and welcome to Technology Today. I'm Lisa Pena. The CubeSat to study solar particles, or CuSP mission, is expected to launch on August 29, 2022. It will be a secondary payload aboard NASA's Space Launch System, the most powerful rocket NASA has ever built. The CubeSat will study space weather, specifically solar particles. Our guest today is SwRI space scientist Dr. Mihir Desai, principal investigator of CuSP. Mihir, the CubeSat launch is coming up. It must be a busy time for you, so we appreciate you taking time to discuss this mission with us today.
Thank you, Lisa. I'm very happy to be here with you and discuss this exciting mission.
So let's start with understanding this unique spacecraft. What is a CubeSat?
CubeSats are small satellites that come in standard forms. The forms are 1U, 2U, 3U, or 6U, where each U is a unit cube about 10 by 10 by 10 centimeters volume. Until about 2014, these small satellites were funded at universities by NSF for research, training, and educational purposes. From about 2015, NASA started funding CubeSats for research, training, and technology demonstration purposes. The Southwest Research Institute proposed the CuSP mission for studying solar particles, which was one of the first ones that NASA selected for flight development in 2015.
And what were CubeSats used for? What did universities use CubeSats for?
Mainly for training their undergraduates and graduates and educational purposes. They also did some research with it, but NSF, the funding amount was not sufficient to do cutting edge research. It was more of a training facility, as it were, for training the next generation of space scientists and engineers.
All right, so definitely some new uses for CubeSats today, and we'll get into that in a minute. But what are the advantages of a CubeSat?
CubeSats are really modular in the sense that you basically buy a frame and you put your systems in it that you want to fly. Of course, that makes it you can produce them in mass and without too much cost. They're also low weight, and launching objects in space is very expensive. The launch costs get inevitably higher for the heavier satellites. This makes CubeSats with each weigh about 1U weighs about 4.5 kilograms, very, very cost effective. They also have very standardized power systems, avionics, attitude control, and all of the subsystems are you can buy them off the shelf. So there are companies that have built them, so that makes them extremely low cost and low risk as well at the same time. And they can be launched in bulk. Many satellites can be launched all at the same time or one after another, which really makes failure of a single CubeSat very, very risky if the mission involves a suite of CubeSats or a fleet of CubeSats.
All right, but overall, they are easy to build, low cost, low weight, and for the most part, low risk. And so these CubeSats have a big job ahead with the CuSP mission to analyze space weather. So how do these CubeSats work? How will they analyze space weather?
Not all CubeSats are designed to analyze space weather. Some are designed to just for technology purposes and other research purposes. But CuSP is actually designed to measure solar particles and the interplanetary magnetic fields that cause space weather. These originate from the sun, and during very active periods when the sun has a 11-year cycle where the activity peaks. If you will, the coronal mass ejections and solar flares occur at the peak of about 1,000 per day, 1,000 per year. Sorry. So they're very powerful explosions on the sun that can cause adverse effects. So the CuSP will be out in interplanetary space in an orbit that is very similar to Earth, but it will be moving away from Earth. So it will directly measure these solar particles and interplanetary magnetic fields that are responsible for increasing the radiation hazards in near Earth environment.
Okay, and aside from solar particles, there are other types of space weather. So what is space weather? What is classified as space weather?
Space weather is mainly for our purposes. The space weather originates entirely from the sun. It's not coming from elsewhere. It's just solar explosions that create solar flares and coronal mass ejections, and those increase the radiation levels near Earth in terms of X-rays, gamma rays, particles, relativistic particles, and those are what we want to try to understand and predict. Mostly, this is electromagnetic radiation and charged particles that can affect human activity and technology as well. As I said, space weather comes in three forms: X-rays and gamma rays from flares, the solar energetic particles, which is the scientific goal of this mission, radiation from flares and coronal mass ejections. And then finally, you get those blobs of plasma, which is known as coronal mass ejections, that hit and interact with the Earth's magnetic field and cause what's known as geomagnetic storms. So all these effects are driven by the sun. There are and these occur mainly during the height of solar activity, as I said, the peak of the 11-year cycle. During the minimum, there is space weather, but it is not as dangerous as what you get during the height of the activity.
You mentioned, some of the adverse effects of space weather, but can you specifically tell us, like, what are the consequences of space weather when it affects Earth? What would we experience here if space weather impacts us?
Right. So X-rays can increase and can affect our communications, our GPS communications, our satellite communications. Solar energetic particles can interact with our electronics and cause single event upsets, what's known as single event upsets. If the radiation is strong enough and very, very sustained for days, which it can be over a period of days, then the radiation in the polar caps increases by quite a lot. And astronauts or airline crew who are doing some activity on the ISS or elsewhere could receive their annual dose in hours instead of the entire year. In fact, polar flying airlines have also been diverted and delayed because of these radiation storms happening in the polar cap regions. And finally, when the coronal mass ejections come in, they interact with the Earth's magnetic field, as I said, and increase the geomagnetic activity. And what they could affect pipelines, they could affect transmission. Pipelines, they could also affect power grids, and they cause outages. In fact, in 1980, sometime in the mid 80s, there was a power outage due to a solar storm in Quebec that knocked out most of Canada's power, most of the east coast of Canada's power grid for a few hours. So there's many effects that we know that are happening because of space weather.
So understanding space weather is important, and understanding how to counteract these effects is important also. So, our daily life could be affected by these events, as you just mentioned. So we talked about the launch date for the CubeSat mission to study solar particles, or CuSP. It's approaching on August 29th. So tell us more about CuSP, which is SwRI's first CubeSat mission. What does this mission hope to accomplish?
Yes, so a little bit of history. CuSP was originally selected by NASA as a 3U CubeSat to fly in low Earth orbit, or LEO, with only the Institute's Superthermal Ion Sensor to measure solar particles over the poles. However, 1 year later, NASA's Space Launch System, or SLS, provided an opportunity for 6U CubeSats to be launched into the interplanetary medium, which is ideally the correct location of where we want to make these solar particle measurements. And this enhances our science return because we are making measurements where we really need to make them without being filtered by the Earth's magnetic field. So the CuSP being proposed and was then selected to upgrade to a 6U, and we added 2 instruments to complete the full range of measurements that we need to understand how particles are accelerated by solar flares and coronal mass ejections. In addition, one of the instruments is a magnetometer, so we measure the magnetic fields of the coronal mass ejection that come about 1 or 2 days later and impact the Earth. So we have a great set of measurements coming up.
So if you can kind of break it down for us. So you get these measurements back. What does this type of data from solar particles reveal? What is it telling you about how we can protect ourselves from the adverse effects of solar weather?
Right. So the main questions that we want to answer is, if a solar flare occurs near the sun, and it's associated with coronal mass ejection, will we get affected at Earth in an hour or 2 hours or 3 days later over the period of time? And right now we have no means of telling whether a solar flare, even though it may be the most powerful solar flare you have seen, will impact Earth in any sense. So what we want to do is we want to measure these particles to tell us to give us critical information about three areas. First of all, what is the material that is actually accelerated in these solar particles, the large events? Second is, how exactly is this material selected and accelerated to higher energy? So the mechanisms of how the particles are accelerated. And finally, how does this accelerated material get to Earth and then finally impact us? So all these science questions are relatively still being explored, even though we've been making these measurements for nearly 30, 40 years. They're still very much unknown, and we are nowhere near the way where we can actually make reliable and accurate predictions of their impact on our society. So that's what we want to learn.
Okay, so it's helping us get a clearer picture of what the issues are and how we can avoid major problems.
Yeah. So, for instance, if there's a flare occurred at the sun, and we know within an hour this is going to impact Earth and cause increased radiation levels. So at that point, if astronauts are doing extra vehicular activity on the lunar surface, they can go into a shielded area. Same thing with the ISS astronauts as well on the International Space Station. They could also go into an area back into where they can be shielded and protect themselves from getting a radiation dose, increasing their radiation dose. So that kind of thing is what we want, but we are nowhere near at even after, as I said, 30 years of measurements.
Okay, so the CubeSats are not just being launched into space on their own. They are actually hitching a ride to space. So tell us more about the CubeSats, the CuSP mission's destination, and how this spacecraft, the CubeSats, will get there.
So CuSP will escape Earth. It's in an Earth escape orbit. It will be ejected before the Orion spacecraft does a lunar flyby, and the CuSP will, if necessary, perform a small maneuver to avoid impacting the moon. After the lunar flyby, CuSP will enter into a heliocentric or sun-centric orbit, just like all the rest of the planets in the solar system, including Earth. So basically, it will be at the location of Earth, which is 1 astronomical unit, same location, but it will be drifting away slowly from Earth, either ahead of Earth, or behind us. And this gives an ideal situation for us to make these measurements in the interplanetary medium.
All right, and it will be aboard the Space Launch System, which is the most powerful rocket ever built by NASA. How did CUSP end up on this rocket? And can you tell us a little bit more about the rocket itself?
Sure. So the rocket is, as I said, the most powerful rocket that NASA has ever built. It took a long time to build, and it cost a lot of dollars because we want to make sure that this rocket can be used for future manned missions, and that makes the quality and the uh, workmanship to be really on of a very high quality, basically, so that you can't have any mistakes. You don't want to have any mistakes like that. So the way we got on that was NASA headquarters decided that this can be an ideal opportunity to do some lunar science, some interplanetary science, and they had an SPAR ring, which is just a ring that can hold the 13 of these CubeSats, and we are one of them. So each SLS or NASA gave each science division one slot to fly on this SLS, and we got selected to do so because our science was greatly enhanced by us getting into an orbit that is in the interplanetary medium. So in some sense, CUSP is really a pathfinder because there has been never been an interplanetary a CubeSat mission, although there was one at Mars, but it hitched a ride with a mother spacecraft, and it's still making measurements in interplanetary space. So in for the heliophysics division of for solar and space weather, CUSP is the first mission to do that,
So
to
that
make
was
measurements in the interplanetary medium.
Yeah, so that was a victory in itself, getting chosen by NASA to move forward with this mission. What did that moment feel like when you got word back that you would, in fact, be aboard the SLS?
It means that see, when you propose something, you hope you win, but when you actually win, you realize suddenly that you got to do the work now, right?
Yeah.
So excitement as well as nerves and everything else that comes with it, all emotions are on the table at that point. But we managed to get the work done. We had challenges during the final year because COVID hit, and we still had to do our testing uh, and integration and assembly and all that, and then deliver it during COVID time. So we delivered in April 2021. Originally we were supposed to SLS was supposed to go in 2017, 2018, but due to the launch delays over the number of years, we basically are going to launch this year, hopefully.
All right, so you got through the challenges, and you're here now. A lot riding on this mission. So the launch date's August 29th. That is the expected launch date. However, if there are issues that day for whatever reason, there are a couple other dates that NASA's looking at to launch. Will you go over that? How that works? If August 29th isn't your date, what happens next?
The next date is to be September 2nd, and the one after that is September 5. After that, I think they have to create a new launch window, and it might be postponed to October if they don't make it on one of those launches. Any number of factors can influence that delay. For instance, weather could be bad that day. There could be some software glitches, and everything didn't really go as well as they wanted to in their test run. So there's a number of ways because ultimately you don't want to blow up on the launch pad and have a failure that way because that would be quite disastrous. So I am planning to be there at the launch. I don't have a role except as a spectator, and all we'll have a lot of nerves, bitten nails.
Yeah,
Um,
I can imagine. It's a big deal for you and your team. So, of course, we'll be rooting for you and the CUSP mission. I'm sure it'll be successful. I did want to talk about your planning for this mission. I know you mentioned it a little bit earlier, avoiding an impact with the moon. So, planning this mission did include an intense launch analysis to do just that, to avoid hitting the moon. There was a real chance of that happening. How did you discover that could be an issue, and how will you avoid it?
So, in order to get into the heliocentric orbit or the sun-centric orbit in an Earth escape orbit, we were originally scheduled to be deployed on after the lunar flyby. But SLS informed us that the Orion capsule and the module might be too cold for any deployment beyond after the lunar flyby. So we had to make a decision and get deployed at an earlier stage before the lunar flyby. NASA also told us that there was a chance, although we will follow the same ballistic trajectory that the capsule would, but there was a chance that we could hit the moon. So the mission operations team at GSFC did a detailed orbital analysis, and basically they will send a command to CuSP to execute a lunar avoidance maneuver. This will basically raise the perigee of the spacecraft as it goes around the moon. So it will still go around the moon, and it will still hopefully get into the heliocentric orbit that we want to get into. So the analysis is done. We are confident that we will not hit the moon, and hopefully we will be able to talk about the successes of the mission.
All right, and tell us a little bit more about the complex scientific instruments CuSP is using to collect data, because those instruments themselves are scientific wonders.
Right. So first of all, they're all miniaturized, the size you can fit in your palm. And they are extremely sensitive instruments to be flying on this mission, because one of them is, as I suggested earlier, is the superthermal ion sensor, or CIS, which is developed using our internal research funds and also funding from NASA as well. This sensor will measure the particles, the material that is being accelerated. If you recall our early conversation, that we want to find out what's being accelerated, how it's being accelerated, and how does it get to us. So what's being accelerated will be measured by our institute sensor, which is the superthermal ion sensor. How it's got accelerated will be measured by the MERIT sensor, which is from Goddard Space Flight Center. These measure the high energy particles that increase the radiation hazards for astronauts and satellites, as I discussed earlier. And finally, the Jet Propulsion Lab's magnetometer is basically the magnetic field that measures the magnetic field along which these particles travel. So that will enable us to figure out how the particles get to Earth. So we are addressing all three of the big questions that I pointed out to earlier when we talked about what's actually needed to make progress in this area.
All right, so we talked about the advantages of CubeSats, but any roadblocks or challenges in using this very unique and small satellite for such a big job?
Yeah, so to fit a fully functioning spacecraft with all subsystems and the three instruments in the small size, which is also known as form factor, is challenging. And of course, it's like fitting 10 pounds of potatoes in a 5-pound bag, right? Other challenges are that the commercial off-the-shelf parts that I talked about earlier, that are advantages in many cases where you just want to fly in the low Earth orbit, require modifications and customization for flying somewhere that they're not used to going, like we are for CuSP in interplanetary space. Budgets are also low. We can't prototype and test parts or build and test engineering models, so we just have to go straight to flight parts, and there are challenges with that, as you can imagine. And finally, as a secondary payload, we are really at the mercy of the primary payload, which in this case is the Orion capsule, which is unmanned in this case, but it will be future. It'll carry astronauts to the moon in the future. Because of the manned rated program nature of the Artemis 1 mission, which is what it's called, SLS had a more stricter requirements program, which meant more analysis, more testing, more documentation, which of course, we were not initially budgeted for. But NASA headquarters has been very, very helpful in helping us out with our cost and schedule all the way. Without their support, we would be in trouble.
So just to clarify for our listeners, so Artemis 1 is the NASA mission. The Space Launch System rocket, the most powerful rocket we've been talking about, is the spacecraft being used in the Artemis 1 mission.
Right.
And our CubeSats are hitching a ride on the Space Launch System aboard that rocket that is part of this Artemis mission.
Yeah.
But our mission is called CuSP, so it's a
Yeah.
mission within a mission.
Yes, it's a secondary payload. There are 13 of us in the hitch to the rocket, between the rocket and the Orion capsule or the Orion module, and we will be going with the Orion module, and then they'll separate the S-power ring and then eject us or deploy us.
All right. So this is SwRI's first but not last CubeSat mission. What does the future hold for CubeSats?
For the Institute itself, we are the principal investigator of a mission called CUBIX. This will measure X-rays from the solar flares. The CUSP mission will measure the particle radiation, the charged particle radiation. CUBIX will measure X-rays from the solar flares. So it's a different aspect of space weather, of course. And then ICOVEX, which is being built in San Antonio, will study the effects of space weather in the Earth's upper atmosphere or ionosphere. Ultimately, we need a bunch of these CubeSats distributed across interplanetary space in the Earth system, near Earth system, so that we can have these CubeSats can track, monitor, and ultimately we need these data to be fed into models that can predict how severe a solar storm and its radiation effects could be on Earth, as well as if we are ever to go deep space into Mars in the next 10 years, then we would need all that information to be available to us at an instance so that we can make these predictions and take precautions.
All right. So this is really the first seed of what will be, or what you hope to see in the future, is a network of space weather stations that's I guess will be constantly relaying this useful data back.
Yes. Part of the challenge of the CubeSats is if you put them too far away, the radios are not powerful enough to communicate beyond a certain distance. So we need to put a big mothership kind of situation where all the CubeSats are communicating with, so that there's only one mothership that communicates the data back to Earth, as opposed to all CubeSats doing their own communications individually, because that could take. I think the deep space network would be overwhelmed. It's already oversubscribed. So that's just to make life easy, you'd want to do something like that, to have one mothership and 25 other CubeSats talking to the mothership, and only the mothership talks to Earth.
So, Mihir, when possible, we like to know a little bit about the person behind the science. So, how did you become interested in studying space weather, and what was your path to this field?
So I actually started out by studying electrical engineering, but I didn't really like the fact that the field was just applied mathematics and applied physics. So I decided to pursue a more pure field, that of mathematics and physics, obviously. Um, so after that, after my undergrad, I worked on Jupiter's magnetosphere for my dissertation topic. And then I went to European Space Agency in Holland as a postdoctoral researcher to work on solar and interplanetary particles. That's when I really appreciated or started getting into space weather, because it allows studying space weather and understanding it allows me to do science that has the potential of providing, immediate benefits to humanity. So that was the motivation for why I went to do space weather. I wanted to study space weather. After Holland, I went to University of Maryland to continue studying solar particles. At that time, the Maryland group had pioneered a novel measurement technique that enabled mass spectrometry to measure composition of matter in interplanetary space at very, very low energies, which is the seed material that I talked about that's being accelerated. And I wanted to learn and work with the best scientists and engineers in the field at that time, and which is why I am now at Southwest Research Institute.
I really like that you said that. You wanted to be in this field because you saw it as a way to provide immediate benefits to humanity. And I always like to point out in our episodes that is the SwRI mission, research and development to benefit humankind. Definitely part of our mission. So Interesting path there. So I want to go back to launch day coming up. You'll be in Florida, is that correct?
Yes.
Okay, so walk us through that day. You're going to wake up. Are you gonna do any last minute checks of anything, or are you purely just gonna go to the site and watch? What does that day look like for you right now?
Well, it could be night. We don't really know when they'll launch, the launch window itself. I don't know what that is. It could be midnight, it could be 2 o'clock, 3 o'clock, whenever, and it could be sometime in the daytime as well. So depending on when it is, either I'll not go to sleep or I'll wake up very early.
Hmm.
And that's okay. And we will be in a VIP area where we'll have a sort of like very close up view of the launch itself. So hopefully we'll be all there, and with my family is planning to go along with two of the other scientists that I work with on CuSP. So we won't do any checks because the whole spacecraft and everything else will be on the launch pad a day before or 2 days before. I don't know exactly when, and nobody will be allowed to go there. So yeah, we'll just be looking at it in awe from afar, basically.
Okay, it's going to be a huge event, and how amazing that you get to be a part of it. This is a once in a lifetime opportunity. So, really amazing. And that's exciting that your family gets to join you to see that. So, I bet everyone's excited. Uh,
Yes, they are.
so, what do you envision as the CUSP mission's lasting contributions to the space community, and as we mentioned, to humanity? What will be the lasting impact?
So besides the progress in this three science areas that I talked about, what material, how it's accelerated, how it gets to us, as of now, our ability to understand, monitor, predict space weather is very, very primitive. It's in the same state as our terrestrial weather prediction capability in the 40s and the 30s and the 40s. We have a few satellites that are scattered in space, uh, pretty much according to the science mission's requirements. There is no coordinated constellation that can track and monitor the space weather. So, our ability to predict space weather and effects on Earth is just, as I said, very limited right now. And we are trying to do predictions from a single spacecraft located somewhere that is not quite appropriate for what we want to do. So we are hoping that with the launch of CuSP, NASA can actually start thinking about launching mission after mission and form a constellation that will allow us to make measurements across the entire interplanetary space to form like a string of pearls in interplanetary space to provide the multi-point measurements that are needed to improve our space weather modeling and prediction capabilities. So I'm expecting CuSP to be the first of many.
Okay, we're excited for you. Bottom line, the findings of this mission will benefit us all and provide insight to avoid disruptions on Earth caused by space weather. So I'm really looking forward to all it will uncover. We'll be following it closely. Thank you for helping us understand CubeSats, Mihir. Best of luck to the CUSP team on the launch and the mission.
Thank you for having me. Pleasure talking to you.
And thank you to our listeners for learning along with us today. You can hear all of our Technology Today episodes and see photos and complete transcripts at podcast.swri.org. Remember to share our podcast and subscribe on your favorite podcast platform. Want to see what else we're up to? Connect with Southwest Research Institute on Facebook, Instagram, Twitter, LinkedIn, and YouTube. Check out the Technology Today magazine at technologytoday.swri.org. And now is a great time to become an SWRI problem solver. Visit our career page at swri.jobs. Ian McKinney and Brian Ortiz are the podcast audio engineers and editors. I am producer and host Lisa Pena. Thanks for listening.